Good morning, champ. Hydrostatics taught us what happens when fluids rest. Now, let's set them in motion. Today, we'll watch pressure, velocity, and height trade energy with each other. The same ideas that made a cube float or a bubble rise now explain why water jets accelerate and why airplanes can fly. Our goal is to derive Bernoulli's equation, the energy law of flowing fluids, and to see that it's really just Newton's second law written for a moving particle of fluid. Before energy, we need mass. Imagine a smooth stream tube, a tunnel drawn by streamlines. Fluid enters one end and leaves the other. Because no mass can leak through the walls, whatever goes in must come out. That gives the continuity relation, rho 1 times area, 1 times velocity 1 equals rho 2 times area 2 times velocity 2. For incompressible flow, density is constant, so we get area 1 times velocity 1 equals area 2 times velocity 2. That's continuity. When the area shrinks, velocity grows. Squeeze a stream tube and the flow speeds up. Now let's look at a tiny bit of fluid sliding along a streamline. It feels two kinds of forces, pressure pushing on its faces and gravity pulling it downward. The pressure on the front face is P. The pressure on the back face is P plus the small change in P along the streamline. Their difference gives a net pressure force that acts opposite to the pressure gradient. Add the weight component along the streamline, minus rho g sine alpha, and apply Newton's second law per unit volume. The result is that's the Euler equation along a streamline. The term dv over dt means the acceleration of a moving fluid particle as it travels through the velocity field. Even if the flow is steady in time, the particle can still accelerate as it moves into faster regions. Along a streamline, dv over dt becomes v times dv over ds, the real acceleration the particle feels. Plug that into the Euler equation. That's Bernoulli's equation. The total mechanical energy per unit volume stays constant in steady, inviscid, incompressible flow. Pressure energy, kinetic energy, and potential energy all swap, but the total never changes. Let's apply it. Imagine a horizontal pipe that narrows from area A1 to area A2. At section 1, the velocity v1 is known. We'll find v2 and the pressure difference. From continuity, v2 equals a1 divided by a2 times v1. Since the pipe is horizontal, z1 equals z2. Bernoulli then gives p1 plus 1 half rho v1 squared equals p2 plus 1 half rho v2 squared. Subtracting p1 minus p2 equals 1 half rho times the difference between v2 squared and v1 squared. Substitute the expression for v2 and we get p1 minus p2 equals 1 half rho v1 squared times open bracket, the ratio a1 over a2 squared minus 1 close bracket. So as the pipe narrows, velocity rises and pressure drops. Pressure energy turns into kinetic energy, exactly what happens in a nozzle or a venturi tube. Let's recap. Continuity, area times velocity stays constant. Euler, forces along a streamline create acceleration. Bernoulli, p plus 1 half rho v squared plus rho gz is constant, and for a contraction, the pressure difference equals 1 half rho v1 squared times the ratio of areas squared minus 1. So champ, Bernoulli's equation isn't magic. It's Newton's second law dressed up in fluid motion. When a fluid speeds up, it loses pressure. When it slows down, pressure builds back up. That's the heartbeat of every jet nozzle and wing on Earth. Until then, keep that math streamlined and your curiosity flowing.